Okay, good. So welcome back. So we will continue this course with nth order linear differential equations. Some general theory we did on Thursday. And today we are going to take up one easy topic, which from my questions at the very end of the last lecture, it looked as if you know this already. At least you could guess all the answers correctly, which is very important. If you're able to guess the answers correctly, that means you have developed some intuition for the subject. And we will do it more formally. That's all that we will do today. So today's topic is in two variable also, we first did the constant coefficients and then we did Cauchy-Euler, right? So two variable, not two variable, the second order homogeneous linear differential equations. Similarly, nth order, we have done some general theory and we will apply the general theory to nth order linear ordinary differential equations homogeneous with constant coefficients. That's a topic for today. So let me start sharing the screen. And as usual, one of you could confirm that you can see it.
Yes, sir.
Yeah, we can see.
Great. So let's start. So today's keyword, as I said, constant coefficients, right? You have these coefficients A1x, A2x, etc. And all of those are constant functions. Okay. So let's start. And once again, let's recall you have answered. So what we are going to do is, in the second order, we had three cases: distinct real roots, equal real roots, complex roots. In distinct real roots, M1, M2, you got a basis to be e power M1x and e power M2x. In equal real roots, you took x power mx and e power mx and then x e power mx. And if you got a plus ib and a minus ib, then you took e power a plus bix and e power a minus bix. But that is not quite correct because we would like to have real valued functions. So you add by 2 and subtract and divide by 2y. So you will get e power ax sine bx and e power ax cos bx. Same strategy. If you will get a characteristic polynomial here, and you find, suppose you are able to find its roots, and if you have the roots m1, m2, etc., then you see whether they are distinct or equal or some repeating and some not repeating. Appropriately, you multiply by x, x square, etc. if there are repeating roots, and if a plus bi, a minus bi is coming, you write it in terms of cos x sin x. Okay, so this is the differential operator where all these coefficients are constants. So if you take a function f in c and I, our operator is of this form, LF, and this is called a constant coefficient differential operator. This just means the coefficients are constant functions. Okay. And so we can write a differential operator like this, constant coefficient differential operator. Suppose you have one more. So this is summation ai d power I, and here you have summation di d power I. My notation is a1 dn minus 1. So I have written dm minus I d power I. And you can easily check that, whether you take the order doesn't matter. The order in which you differentiate doesn't matter. Because of our assumption that the function is in CNI. Okay, so the derivative exists and the derivatives are continuous. So you know Clairaut's theorem or mixed partial, whatever. The order in which you take derivative doesn't matter. dr composed with, so I write product, but this means composed with. So dr composed with ds is same as ds composed with dr. And therefore you have L composed M is same as M composed L. In other words, L and M commute. Okay, L and M commute with each other. The order in which you apply, this is not in general true for functions and compositions, right? Composition is not commutative. So this is a particular case because you have constant coefficients, you are getting commutativity of these operators. In general, you should not expect differential operators to commute. This is a very simple case where you have abelianness, commutativity. Okay, for any f for which these make sense. In particular, what is C infinity I? What is this notation? I never told you this.
They can be differentiated as many times
As
as
many times as possible. Okay, so some people call it smooth function, infinitely many times differentiable. So in the second order constant coefficient case, just recalling, we looked at the characteristic polynomial of the given differential equation. And what will be the characteristic polynomial here in the nth order situation? So what did you do there? You substituted e power mx and then you solved and you got a quadratic, right? So if you had y double prime plus pxy prime plus qy equal to 0. If you put e power mx, you will get m square plus pm plus q. What will be the characteristic polynomial in this case? If this is your starting equation, okay, maybe I can take constant coefficient. So assume that a naught is 1 and a1 etc are there. What will be the, so what will you plug in order to solve? You will plug in e power mx, right? And when you plug in e power mx, what will happen here? Here you will get m times a1 and next you will get m squared. Is that correct?
No, sir.
No,
Here you
sir.
will get m power n
And
minus
and
m power n minus 1. Next, you will get m power n minus 2. And here you will get m power n. And here you will get m and here you will get nothing. So what will you cancel? So how will you do this now? Yeah, so that is your, so e power mx will be there. E power mx you can cancel because it is never 0 and therefore you have got a polynomial in m. That is your characteristic equation. Okay, so if this is the operator, we define this to be the characteristic polynomial, right? If you substitute e power mx, what you will get is exactly PL at m. That is easy to check. So this is defined as a characteristic polynomial. And then we are interested in analyzing the roots of it. But let us make one observation. Suppose L and M are two constant coefficient linear differential operators. Then first observation is that L equal to M if and only if the characteristic polynomials agree. So if L equal to M, then it is clear that PL equal to PM, right? Because PL, the coefficients of PL are exactly the coefficients of L. So if L is this and there is M which is B naught, D power N, etc. If L equal to M, then of course PL equal to PM. But the other way also we want to conclude. If PL equal to PM, then L equal to M. Okay, so that is also true. We will show it. And this is obvious. The characteristic polynomial of the sum of two constant coefficient differential operators is sum of the characteristic polynomials. That just follows from the definition. If you have b naught, d power n, etc., if you add, it will be a naught plus b naught, etc. So characteristic polynomial also, it will be sum. And similarly for product, again obvious. And similarly for scalar multiplication, again obvious. The only thing which needs a little bit of proof here is first one direction. If PL equal to PM, then you have to conclude that L equal to M as operators. Okay, but that's also very easy. So 2, 3, 4 are obvious. And the proof of 1, if L is this and M is this, then PL is this and PM is this. That's a definition. Okay, so I made a confusing statement. The obvious thing is if PL equal to PM, if PL equal to PM, yeah, I said it the other way. I was not really thinking, but the obvious thing is if PL equal to PM, then two polynomials are equal. If two polynomials are equal, what does that mean? The coefficients are equal and therefore the coefficients are equal and therefore L equal to M. That is obvious. If L equal to M, then you have to show that the characteristic polynomials are same, but that's also easy because L equal to M means L of F equal to M of F for any F. That's the meaning. And you plug in e power mx and you would have solved the problem. So in particular, it is true for e power rx and therefore you will get an minus I ri e power rx is bm minus I ri e power rx and You can cancel Ri. No, sorry. So you can cancel e power Rx. You can cancel e power Rx. No, can you cancel e power Rx? No. You will get this. Yes, of course you can cancel e power Rx. I is the variable. And if you cancel e power Rx, you will get summation an minus I r power I equal to summation bm minus I r power I. And this is true for any r. This is true for any r. That means the polynomial PL equal to the polynomial PL. Okay. So this is also easy, but one small step is required. If L equal to M, then LF equal to MF for each F. And in particular, you take the function to be e power Rx as R varies. And you would have concluded summation an minus I r power I is summation bm minus I r power I for every r. And therefore, as polynomials, they are equal. Okay. A corollary is if you have three constant coefficient linear differential operators, and suppose the characteristic polynomial of L is the product of the characteristic polynomials of the other two. What can you conclude? Can one of you tell me? What can you conclude from this about L and M and N?
L equal to Mn.
And what is the meaning of Mn once again? What is the meaning of Pm times Pn? What is this dot here, the central dot? Multiplying two polynomials. So that is product. And in Mn, what is the meaning of Mn?
We are doing the same. Multiplying those two operators.
Two operators. So it is composition. Okay. It is composition of two operators. And what did you say? L equal to M composed with N, right?
Yes, yes.
Yes. And what is the proof? Proof is Pm times Pn is obviously same as P of Mn. Therefore, PL equal to PMN, and we proved that if PL equal to PM, then L equal to M. So from that it follows. So L equal to Mn. In particular, if PL is this, the polynomial, suppose you are able to factorize and you got this factorization, then what can you conclude? So this is product of how many polynomials here? This is constant polynomial. If you count n plus 1 polynomials, this is just constant. So that constant will remain as constant. And then you have all these polynomials. And what is the associated differential operator to x minus r1? Associated operator is
e power Rx.
Say that again.
E power Rx.
No. I'm asking what is the operator for which the characteristic polynomial is x minus r1? What is the constant coefficient operator for which the characteristic polynomial is x minus r1?
We could replace x by d.
Yeah, exactly. D minus r1. Okay. So what we have concluded is L equal to A0 times D minus r1. I shouldn't say times, composed with D minus r2, composed with D minus rn. Okay. This is a corollary to the corollary, because for if product of two, if this is true, then any finite product, this is true, and you are applying to this n many finite products. So this is product of linear factors, and therefore this is composition of linear composition of degree 1 order 1 differential operators. Okay, so this is good. So this we already proved verbally. So if you have this linear operator, because of this result, you can, without thinking, you can factorize. What will be the factorization of d square minus 5d plus 6?
Minus 2 into d minus 3.
D minus 2 into d minus 3, but keep in mind into means composition, right? Into means composition. So d minus 2 composed with d minus 3. Why not d minus 3 composed with d minus 2? Is that correct?
Yes, both same.
Both are same, because these are constant coefficient operators. It commutes. The operators commute. So both are same. Both as functions, both are same. Okay, so this is d minus 3 composed with d minus 2 or d minus 2 composed with d minus 3. This requires a proof, right? And this follows because we have made this observation. Otherwise, you cannot immediately factorize like that. Given a linear operator, you cannot immediately factorize like that. But your obvious factorization technique works because we have proved this. Okay. Now suppose you have a linear operator which you can factorize as a composition of k many operators, where AIs are also linear differential operators with constant coefficients. So L will also be constant coefficient. And is this obvious that the kernel meaning the null space of AI is contained in null space of L, and that is true for any I. If you take any I from 1 to k, then the kernel of AI is contained in kernel of L. How many of you see this? Can you give a proof? Okay, let us do the easiest one. Suppose I equal to k. What is the meaning of kernel of AK? That consists
Null
of
space
functions
of
such that AK at f is 0. AK applied to f is 0. So if you take f from in AK of f is 0, and you have to show that L of f is 0. Is it clear that if AK of f is 0, then L of f is 0? That's what you have to show. Is it clear?
Yes.
Yes. Why? Because L is this composition, and your L of
Yeah,
f will be AK of f, apply AK minus 1, apply AK minus 2, etc. But if AK of f is 0, then any linear operator will take 0 to 0, right?
In remaining, no need to check it out.
Yeah, so yeah, correct. Yeah, so I'm still reaching there. So if AK of f is 0, then the next things you are applying at 0, at 0, at 0. So L of f will be 0. So for AK it is true. But what if it was some in-between thing? Why did you say remaining no need to check?
We can always rearrange.
Zero,
You can
then
rearrange.
it will become
Exactly,
whole.
absolutely. So if it was A2 that you have to show, you rearrange so that A2 you bring to the right, because these are commutative, and therefore our proof works. Okay, so this is clear, and that's what I have written down here, which I can skip now. So what is the meaning of this? I'm removing AI from here and putting AI here. This is the rearranging, and therefore this is 0. So one line proof. Okay, so this means that f is in NL. So here you are using the fact that a linear operator takes a 0 vector to the 0 vector. Example, find a basis of solutions of this differential equation. So what is the corresponding operator? Corresponding operator is d cube minus 7d plus 6. So what is its factorization? You have to factorize the polynomial x cube minus 7x plus 6. Can somebody tell me the roots? I have chosen a polynomial so that you can easily do it. So tell me the roots.
X 0, 6 and 1.
0, 6 and 1, is that correct? So 1 is correct. 0 is also, no, 0 is not correct, no? X
E
cube
power
minus
x,
7x.
e power 2x, e power 3x. I think.
1 minus 3 and 2.
Minus 3 and 2. Okay, so 2 cube is 8. 8 minus 14 is minus 6 plus 6. That is true. And 3 minus 3, right? Minus 3 is also correct. Yeah. So this is the thing, and this you factorize minus 3 and 2 and 1. And therefore you have got this factorization, d minus 1 corresponding to this, d minus 2 corresponding to this, d plus 3 corresponding to this. And how will you get a basis? What did we conclude from the previous result? The kernel of this is contained in kernel of L. So you want to get a basis for the kernel of L. And by dimension theorem, you already know that there are 3 things. So you have to find a basis for each of this. That's enough. So d plus 3, can you give a something in the basis of d plus 3? What is there in the null space of d plus 3? What is killed by d plus 3? Of course, you know this.
E to the minus
E
3.
power
minus 3x.
Now the question is, is e power minus 3x in the kernel of L? Yes, that is the previous result. Now, what is the kernel of, give me the obvious element in the kernel of d minus 2?
E to the power 2x.
By the previous result, that is also in the kernel of L. And in d minus 1?
E to the power x.
By the previous result, that's also in the kernel of L. Is it true that e power x and e power 2x and e power minus 3x are linearly independent?
Yes. Yes.
Therefore, they form a basis of L, null space of L. So that's how it is done. So this is there, this is there, this is there, and these all are there, and they are linearly independent. So you have got a basis. Okay, so this is the strategy. So you have understood everything. Why is this a basis? Because of this difference of the coefficients, you can show that these are all linearly independent. How will you quickly show it's linearly independent? You write a times this plus b times this plus c times this is 0. Differentiate once, you will get something. Differentiate once more, and you can say that the otherwise you know Wronskian. Wronskian is clearly non-zero. So that will do the job, and therefore the general solution is like this. So this illustrates a general case. We have, proved a general case, including if they are real roots, we are done, right? Suppose, you have nth order thing, and suppose you have M1, M2, etc. Mn are distinct roots, then you have done, right? E power mix will belong, d minus mi corresponds to e power mix, and e power mix will be there. And because the mi's are distinct, they will form a basis. So we have already proved a theorem that if the characteristic polynomial has distinct roots, then you have already obtained a basis of the solution space. Okay, so if you have this, then what is the basis? Basis is e power r1x, e power r2x, etc., e power rnx, and we have proved this. I did not give the proof here, but we detailed the proof in one example, and that's the same proof. Okay, what if it has repeated roots, and you know the idea, you will have to multiply by x, x square, etc. So in the n equal to 2 case, if m1 equal to m2 equal to m, then you only got e power mx. This is not minus e power mx. This is just hyphen. Okay, so it is just e power mx. And the other one you found by the method of looking for a solution of the form v times f. We had this method, and that process gave us x e power mx, and this gives us a clue as to what should happen now. So let's do the following. For any real number r, if you consider the function e power rx, x times e power rx, etc., x power m minus 1 e power rx, they are all linearly independent. And this is easy to check. And next observation is, these are all linearly independent as simple linear algebra. You can check. These all belong to kernel of which operator? D minus r power m. What is the meaning of d minus r power m? D minus r composed with d minus r composed with d minus r, etc. m times. And so what do we need to check? You need to check that, is it clear that e power rx belongs to the kernel of this? Is it obvious? Yes, because d minus r itself kills it, right? E power rx is annihilated by, is killed by d minus r itself. So d minus r of e power rx is 0. So d minus r further, if you apply at 0, again it is 0, 0, etc. What do you think about x e power rx? Will d minus r work? What is d? So one of you tell me, what is d minus r applied to x e power rx?
It will give e power rx.
Yeah, and then you apply one more d minus r, and therefore it
becomes
is
0.
So d minus r square will kill x e power rx. Similarly, by induction, this will be killed all the way if you take up to d minus r power n. So we have proved this proposition. Okay, so proof is written down here. Linear independence is obvious because this is clearly linearly independent. We need to show that these functions are there. M equal to 1, you verify. This is true. And m equal to 2, u1 is in the kernel of this. So it is in the kernel of d minus r square, no problem. U2 you have to do. So you do this computation. This is what some of you have already done. This is d minus r applied to d minus r of x e power rx. And the d minus r applied to x e power rx as e power rx. And that is killed by d minus r. So this gives you the proof. By induction, it is done. So proof in general is induction. If you assume that these many things are there in d minus r power m minus 1, I have to show for m. I have to show for m. These are in d minus r power m minus 1. You can assume by induction hypothesis. We need to show that these are in d minus r power m. And these are in d minus r power m is obvious. Why? Because these are already in d minus r power m minus 1. So d minus r power m minus 1 will kill all these things. And d minus r of 0 is 0. So this is obvious. So only thing to check is um is there. And for that, we compute this, which is d minus r m minus 1 of d minus r of this, and that you do, and you will get d minus r of m minus 1 times x power m minus 2 e power rx, which is um minus 1, which is there in the kernel of this by induction, and therefore this is also 0. Okay, so we have proved this. So if you have characteristic polynomial, now you know multiple roots are there. R1 comes E1 times, R2 comes E2 times, and RL comes EL times. Can you guess the basis now? So kernel of this will corresponds to kernel of the operator D minus R1 power E1, kernel of D minus R2 power E2, etc. And we have already proved that the kernel of L is given by kernel of d minus r power e1 is given by these many functions, right? This is what we just proved. And kernel of d minus r2 power e2 is given by how many functions? Basis e power r2x, x e power r2x up to x power e2 minus 1 r2x. And similarly for en. So we have proved. How many functions are written down here in the display? How many functions are there? How many are there? E1, so this is 1 to E1 minus 1. So that is, no, this is 0 to, this is 0 to E1 minus 1. That is E1 many. This is E1 many. And this is E2 many. So E1 plus E2 plus EL. But E1 plus E2 plus EL is N. So you've got the required number of, linearly independent things. So that's a basis. So the point is that these functions are linearly independent. Okay. You have to check that this whole thing together is linearly independent, which you can check. Okay, so you have to show that this together is linearly independent, which will be helped by multiplication by x when repetitions are there, and then R1 and R2 are different. All these put together, you can verify that these are linearly independent, and therefore you have got a basis. So this you should check, you should check that these functions are linearly independent. So that I leave it to you as a linear algebra exercise. Let's do an example. Can you do this? So obviously, there must be a repeated root. Can you factorize this? The polynomial is x cube minus x square minus 8 minus 12. What are the roots? What are the roots?
-2 is a double root of it.
-2 and? Could you say that again?
2 and -3.
Okay, so let us check. My 2 and -3. 2 is coming twice and -3 is coming once. I hope this is correct. I haven't checked. But you must have checked. Anyway, it's easy. So what are the corresponding? So tell me, what is the basis? Basis will have 3 elements. Give me the basis. X minus 2 whole square will give you e power 2x and
X e to power
x e power 2x, and x plus 3 will give you e power minus 3x. Okay, so this is very easy. So this is a general solution. E power 2x, x, yeah.
2 is not a root, right?
Plus 12, I guess.
It should be -2 and
2 is not a root. Okay, so 2 cube is 8. 8 minus 4 is 4. 4 minus, yeah, 2 is not a root. Is -2 a root? -2 cube is -8. -8 minus 4 is -12. -12 minus 12 is -24.
I guess it should be plus 12.
Plus 12 would give 3 roots.
Plus 2 will give 0.
Plus 12 plus 12.
Plus 12.
The constant coefficient.
Constant of the polynomial.
Oh, here it is plus 12. That's what you're saying?
Yes, sir.
Okay. So let's keep this as it is, and I will correct the typo here. Okay, so this should be a plus. This should be a plus. Okay, fine, good. So thank you. So I need to correct 2 typos, 1 plus here and 1 plus here. Then is it correct? So 2 cube is 8. 8 minus 4 is 4. 4 minus 4 plus 12 is 16 minus 16. That is correct. And minus 3 is minus 27, minus 9, minus 27, minus 9 is minus 36. And no, I'm unable to do the calculation. Could you please check minus 3 is correct?
Sir, just check the sum of the roots. Whether
Yeah,
it's
okay,
correct.
good. Anyway, for this gives you a 4, and 4 plus 4 into 3 is plus 12. This is correct. Yeah. And 2 plus 2 minus 3 is 1 minus 1. Yeah, absolutely. Yeah. So plus 12 here, plus 12 here. I'll correct it before putting it on model. Okay, very good. One more example. So again, yeah. So how do you do this? Though this is 6 degree, it is not very difficult because some roots are obvious. So this is d square is coming out, and then you have a 4th degree polynomial. Let us just check so that I don't make a typo. Is this correct that these are roots? Can one of you confirm that 1 and minus 1 are roots? 0 is of course a root.
Yes, sir.
And 1 is a root because 1 plus 2 minus 2 minus 1, and minus 1 is also a root because minus 1 minus 2 is minus 3, and 2 plus 1 is 3. Yeah, these are roots. Of course, you have to check whether it is repeating correctly, but maybe you can check. If there is a typo, please let me know. I will correct it later. So kernel of d square is, this is interesting. What is kernel of d square? What is
1 over x.
Say that again. You said it. I think you are right. Please repeat.
1 comma x.
1 comma x. Yeah, e power 0x is 1. So 1 comma x. And kernel of d minus 1 is e power x, and kernel of d plus 1 cube is x. No. E power minus x e power minus x square e power minus x. So you are done. Okay, so this is what this is all that is there. So what if complex roots come? Same strategy. In the second order case, if you have a plus ib and e2 minus ib, a minus ib, then you got a basis e power ax cos bx and e power ax sin bx. And if this has a complex root a plus ib, then of course it has a root a minus ib also, because they come in pairs. And therefore x square minus 2ax plus a square plus b square is a factor. And this the roots, right? This the corresponding operator. What are the solutions? E power ax cos bx and e power ax sin bx will be solutions. So this has a basis e power ax cos bx and e power ax sin bx. So similarly, for all the degree 2, not the degree, but the order 2 things, you can give a basis. And so if a plus ib has a multiplicity m, then how will you get it? What should be the strategy? If a plus ib comes twice, and if a minus ib also comes twice, first time you got e power ax cos bx and e power ax sin bx. How will you account for the repetition? What is the strategy?
X
Multiply by
x.
Absolutely.
Multiply by x.
So you need to consider this power m, and you have guessed it absolutely correctly. You will take multiply by x square up to x power m minus 1, and then similarly for sin bx. And exercise, you need to check this. So how will you check this? Check this using induction. Exactly like earlier we have checked this. Okay, so I leave it as an exercise, and let's do one example. So you take the characteristic polynomial. Maybe one root is easy to guess. That's the point. So the characteristic polynomial. So you please verify. One of you should please do this. Okay. And I haven't done this recently. This is from long ago. But do this, and if there is a typo, I will correct it. Okay. Hopefully this. So if you get this, what is the factorization of this? Factorization of this is 4 plus or minus root of minus 4. So 4 plus or minus 2i by 2. So 2 plus or minus i. So what are the roots? X minus 1 corresponds to e power x. Here you get 2 plus I coming twice and 2 minus I coming twice. So 2 plus I leads to e power 2x cos x, e power 2x sin x. It's repeating, so multiply by x. So e power x cos x, x e power x cos x, e power x sin x, x e power x sin x. So very easy. Okay. So I think that's all that I plan to do today. So I'm stopping much earlier than usual, but we can have a discussion session right now. So if you have questions, you can ask me. Otherwise, we can end earlier. Anyway, we will have the interactive sessions on Tuesday and Thursday. Okay, so
Sir, it should be e power 2x.
Yes, absolutely. Yeah, again a mistake here. So e power 2x, and yeah. So let me. So how many typos to correct now? 2 earlier, and here 1, 2, 3, 4. So 6 things. Let me correct it in front of you. We have time, and this is fun. So let us also verify how. What do you see now?
Blank.
Blank. Blank, or you see the Zoom page,
Zoom page.
and you
Zoom
see
page.
video. You see my video?
No.
No?
Yes.
Sir, your video is
Yes,
visible
sir.
now.
We can see.
Yeah.
Video is visible.
Screens.
It's
Good. I was just double checking. Now what I'm going to do is I'll type these. I will not type it. I'm making so many English mistakes. I will correct these typos. I was saying that I will type these. Yeah, I will correct these typos. So maybe once I did it in front of you, right? But I think at that time you could not see. No, last time when I corrected typos in front of you, could you see the corrections? You remember
yes.
this?
Yes, sir.
Now share screen and correct, sir. No problem.
That's what. So you could see. So
Now once share screen and do it.
now are you able to see the?
No, it's green.
Yeah, I will have to share the desktop. Can you see it?
Now, yes.
Yeah, now it's we can see.
So then this is my input. How many of you know LaTeX? Some of you know this way of typing. So
Yes,
you
sir.
can call this, and yeah, are there people who know LaTeX?
Yes, sir.
Okay. And
Yes.
anyway, it's a good thing to learn because in your final year, you may have a project report to type and all that. It's good to learn by that. And do you kind of recall where was the first typo? That -12 to +12. -12 to +12. Where did it come? After this? Yeah, here, no?
Yeah, this page.
This is the first typo. So I need to resay. So let me search for find the general solution. Yeah, so I have reached there. So -12. Is the font big enough? Can you see what I'm changing, etc.?
Yes.
You can see.
I changed to plus there, and once more, I changed to plus there, and I compile, and you should be able to see the corrected PDF. All these are being recorded also. Okay, let it be. It's anyway fun. So yeah, that is +12. Here also it is +12. Now everything is correct on this slide. So those typos are corrected. And then at the very end, no? Hopefully there's no typo.
Yeah.
Here. At the very end, only here, right? 2 + I, 2 - I is correct. That means at the end I have to add 2x. So first one is e power x is correct. In the next one, I have to add 2x here. And 2x here. And 2x here. And 2x here.
If you didn't keep brackets, then it will be something other.
Say that again?
If you didn't keep brackets for 2x.
Yes, I will show you. Okay, let me do the correct thing first and I will show you the wrong thing after that. Can you guess what it will be? If I don't put those curly brackets?
E square and down x.
Absolutely correct. Yeah. So now the typo is corrected, no? So if I did not do that, let me do it here. If I did not do that, then e power x was there. By the way, in order to make compiling fast, let me remove all the pauses, which you can do by going at the very starting and typing handout here. So handout meaning a printout that I'm giving, no? So there you don't want to get all the pauses. So this is how I put it on Moodle. Okay, so I'm teaching you later. Okay, so now see, no pause. So some 250 or whatever has come to 19 pages. So this is how e power x was. And then I said there is a typo, and then I put 2 and I put bracket. Suppose I did not put bracket, then it will be only that 2 will come in the superscript, that x will come down. Okay. So in order to make it, I have to put curly bracket here. Yes, I have to put inside curly bracket. X will go up now.
Okay, sir.
Okay, very good. Yeah, anyway. So whoever missed the lecture on YouTube video, also you can see the tech part of the lecture. Let me stop recording now, stop share. So all the things are, I can also upload on Moodle in front of you, but then I might reveal my password. So let me not do that. Okay. So I may not, no, only dot, dot, dot will come, right? But still, you may see how many digits in my password, etc. So let me also share screen. No, stop share screen, and let me also stop the recording, and then we can have a discussion if you want, and then we will stop.